Okay. A lot of computer problems in the first class, so I'm re-recording this lecture, and I have to use the webcam microphone, so I'm going to stay primarily on this end of the classroom, hopefully, so the microphone can pick it up. I know that works better for you over here, not so well for you. If you want to change positions, that's fine with me. You don't always have to sit in the same seat, that's okay. We have a homework assignment due on Thursday, so if you haven't already started on that, please get started. Make sure you understand how to do these problems. We're going to go through several examples in class that should help clarify the last couple of sections for you. We're talking about today the entropy balance, which we've touched on earlier, but we're going to look at it in more depth today, how mass interactions, work interactions, and heat interactions actually factor into this entropy balance. I had a lot of questions in the first lecture that were good questions about how it happens that you can generate entropy during a process even if there's no heat transfer, or if the system is steady state, or some of these examples that we look at, that there's no energy accumulation or mass accumulation in the system, yet somehow we're generating entropy with this process. And it's important to remember that although we're talking about an entropy balance today, that it doesn't balance in the same way that mass and energy do. That you cannot create mass, you cannot create energy, but you can create entropy. The bad thing is you can't destroy entropy either. So you can create it, but you can't destroy it, which means that the entropy of the universe is always increasing. And this has driven philosophers mad, this idea that the entropy is always increasing. So keep that in mind, that if there are things that don't make sense or are confusing, it's because it's contrary to what you've already been taught, that 1 + 1 = 2. Well, with entropy, that's not necessarily the case. I mean, it does balance out in that in an arithmetic formula that the parts will equal one another, but you can't think of it in the same way as mass and energy, where we can actually create entropy during the process. So it can be a little bit tricky and confusing, but hopefully I can sort it out. So the entropy balance is similar to mass balance, except for we have this additional term in here, this entropy generation term. So we have the entropy entering minus the entropy leaving plus the entropy generated is equal to the total change in entropy of the system. This entropy generation term only comes into play during an irreversible process. So if we're undergoing a completely reversible process, we're not going to be generating any entropy, which is part of where I think the confusion comes in, that in that case, in a reversible process where we're not generating entropy, then it looks just like mass balance, looks just like energy balance. We don't have this additional entropy generation term. However, during an irreversible process, we have irreversibilities in that process that we generate entropy by performing the process. Okay, so due to the fact that the system is irreversible, or the process is irreversible, we're generating entropy. Entropy is a property value when you're looking at it in the table. So water contains, at a certain temperature, a certain pressure, will have a certain level of entropy, and that's based on the absolute zero level of entropy. And it doesn't change unless the system changes, okay, in some way. So for a steady state system, this change in entropy of the system is equal to 0. And if the properties are not uniform, we have to know exactly how the entropy changes for each section of mass as we're looking at it in the control volume. But we don't do that in this class. That's just mostly in there for your information, that on a whole, we assume uniform property values, so we don't have to calculate some integration across the cross-section or across the thickness of a material, that we just assume that it's uniform and we don't have to take into account any variation. So there are two ways that entropy can be transferred into and out of a system, and those are by heat and by mass transfer. You notice that work is not included, okay, because entropy is not transferred to and from a system via work. Entropy generation can be a manifestation of an irreversible process. So if there is a work process that, let's say, generates friction, or during the process you have irreversibilities such as friction, those are manifest in terms of the entropy generation of the system. So it's not transferred into the system by the work, but the irreversibilities are generating entropy, if that makes sense. Okay, so entropy transfer by heat, that if we add heat to a system, we increase the entropy of the system. If we remove heat, then we decrease the entropy of the system. And if our boundary is isothermal, it reduces down to this. So the entropy transferred into a system due to heat is just equal to the total amount of heat transfer divided by the temperature at which that heat transfer occurs. If the temperature is not constant, we either need to know this functional relationship between Q and T, or we can sum up all the individual components of the heat transfer and divide them by the temperature at which those components of heat transfer occur. So say, for example, we'll do an example in a minute of a wall, and we're transferring heat into the wall at a certain temperature and out of the wall at a different temperature. Okay, so in essence, heat is being transferred through the wall, coming in at one temperature, coming out at another temperature. Okay, so then we would use this summation term. We'd look at the heat transfer into the wall at the temperature at which it's being transferred into the wall, and then the heat transfer out of the wall at the temperature which is being transferred out of the wall. So this is a way to get around this integration, that if we can assume uniform property values at different parts or different areas of the system, then we can just say, okay, maybe it's not completely isothermal, maybe there's a small temperature gradient, but we're going to assume that it's this average temperature, and we're going to look at the heat transfer through this area at this average temperature and use that to calculate our entropy term. We do a lot more of that in heat transfer than we do in this class, so you'll see that later if you continue on. So Q sub K is the heat transfer at location K with the boundary temperature of T sub K. Mass contains entropy, so it's like any other property value, that there's a certain amount of entropy associated with a fluid, or maybe it could be a solid or something at that temperature and pressure. And it's proportional to the mass, so if we multiply the mass by that property value, then we can find the total entropy associated with the mass. As we bring mass into the system, we add entropy to the system. As mass leaves the system, we decrease the amount of entropy in the system. And again, if the properties of the inlet and the exit are not constant, then we have to know, again, the functional relationship between the properties, how they change linearly or in an area. But generally, we just assume that it's uniform, and so we don't need to know the functional relationship or numerical model for these property values and how they change over the surface of wherever our mass is flowing in or out. So that's just mostly there for FYI. There is no energy transferred by, or entropy transferred by work. So energy can come into the system via heat and work, but entropy cannot. And this gives further evidence for the distinctions between the first law and the second law. So first law, heat and work are equivalent. Okay, they're just numbers that balance out in an equation. But if we're looking at the second law, they're not equivalent, because we look at the quality of energy. Work is a higher quality of energy than heat. And the higher temperature the heat, then the higher quality it is. But in general, work is more reversible than heat transfer. Okay, so it does make sense that any entropy transfer coming into or out of the system would be via heat, which is always an irreversible process. There may be some irreversibilities associated with the work, but again, that's a function of the process, and it shows up in our entropy generation via friction or chemical changes or things like that. Okay, so the second law tells us that heat and work are not the same thing, they're different. That although they may balance numerically, you have to know what direction, what quality this energy source is in order to determine if a process can really happen. And if a process occurs in the direction of decreasing entropy, for the system and the surroundings, then it's not a real process. And although it may satisfy the first law, it wouldn't satisfy the second law in that way. So let's do an example. And this problem, there's some extraneous information. The dimensions are not needed necessarily. Again, I think this author also has a heat transfer book, and he pulls some of his heat transfer problems and puts them in here. So in this case, we're given a heat transfer. If we were not given this heat transfer and we had to calculate the heat transfer, we would need the area, but we don't need the surface area. So we're going to model a person as a 30 centimeter diameter, 170 centimeter long vertical cylinder with the top and bottom surfaces insulated. So they're wearing like a hat and shoes, or they have lots of hair. And so heat is being shed from the sides of this person at a temperature of 34 degrees Celsius. If the rate of heat loss from this man to the environment at 20 Celsius is 336 watts, determine the rate of entropy transfer accompanying heat transfer. Okay, so rate of entropy transfer. What do we know about entropy transfer? How is entropy transferred?
Heat,
By
mass.
Heat and mass. Okay, so do we have any information about this man's mass changing? Is he spitting or eating or something else? No, we don't have any mass transfer in this problem. So the only way that entropy can be transferred is via heat. Okay, what is our system? A man. Okay, so let's look at this in terms of the energy or entropy balance. S dot in minus S dot out plus S dot gen is equal to ds dt. Is there entropy coming into the system? Do we know anything about being heat transferred to the man? Not really. Okay, entropy leaving the system? Yep. Is he generating entropy? Yeah, he's not reversible, right? And is his entropy changing over time? It may be, we don't really know. We're going to assume that his body functions are operating at steady state conditions. Okay, so the change of this entropy of this man over time is approximately balanced by his metabolism. So he's losing some heat, but his metabolism is eventually needs to eat. But at this moment in time, we're just going to look at that as.
So why is there entropy generation?
There's always entropy generation unless it's a reversible process. So being alive is not a reversible process, right? We can't age backwards like Benjamin Button, unfortunately. Okay, so then we can say that this S dot gen is equal to S dot out. Okay, this is the term that we're concerned about, that we're solving for in the problem. We want to determine the rate of entropy transfer accompanying this heat transfer. So this S dot out term is going to be equal to Q dot out over T. Okay, now which T do we use?
Degree.
20 degrees? Okay, so do we use the temperature of the surroundings or the temperature of the man himself?
The man.
Okay, so it depends on what we're looking at, right? So right now we want to know the rate of entropy transfer accompanying heat transfer. It doesn't specifically say the rate of the man or the rate of the surroundings or whatever. So if we look first just at the entropy transfer from the man to the surroundings, so Q dot out over T of the boundary or T of the man. Okay, so that's 336 watts divided by 307 Kelvin, always converting to Kelvin when it's a temperature, a single temperature. Delta T in Kelvin is the same as delta T in Celsius, so there's no conversion needed. So 336 over 307 is 1.09 watts per Kelvin. And will it be a net negative or a positive entropy transfer? So if we're looking at the man, is his entropy negative or positive? Should be a negative, right? Because Q is leaving. So Q out over this T, it should be a negative value, right? Negative Q out. Okay, so we could also look at the entropy change of the man plus the surroundings. So if we were to look at that, we would have to look at the change in entropy of the system plus the change in entropy of the surroundings. And in this case, it would be Q dot out over T sub B, that's a negative, plus Q dot in over T of the surroundings. And if we put in the numbers for that, we get a negative 1.09 watts per Kelvin plus a 1.14 watts per Kelvin. So the net change is 0.05 watts per Kelvin. Entropy is always increasing. Okay. So that is because of irreversibilities in the system and in life. So we've talked a lot about that before. And entropy generation gives us some metric where we can compare processes one to another and see how irreversible they are. So if entropy generation sort of indicates the degree of irreversibility, we can seek to decrease the amount of entropy generation in order to make a process more wholly approximate a reversible process. Okay, so as we're trying to maximize energy, maximize work output or minimize work input, another way of doing that is by minimizing entropy generation. And again, if we're looking at entropy generation from the energy balance equation, we're just looking at it in terms of the system, not the system plus the surroundings as we did here. And then for an internally reversible process, entropy generation is equal to 0. So we will not have any entropy generation if our process is reversible. That's because irreversibilities are what lead to entropy generation. So in general terms, the entropy balance can be seen in several different ways. S in minus S out plus S gen equals delta S. And if it's a reversible process, then the entropy generation term goes away. So we just have the S in minus S out is equal to the change in entropy of the system. And if it were, like, for example, a reversible steady flow process, then S in would be equal to S out, or S dot in would be equal to S dot out. Okay, so let's look at the difference between closed and open systems. In a closed system entropy balance, the only contributing factor to entropy change will be heat transfer, right? Because work doesn't have any entropy associated with it. There's no mass flow, so the only contributing factor can be the heat transfer. So the entropy equation can be written as the sum of the heat transfers over their temperature at which they occur, plus S gen is equal to the change in entropy of the system. And if it happens to be an adiabatic closed system, then the entropy generation is just equal to the change in entropy of the system. So there's no contribution due to heat transfer, but let's say it's like, for example, a piston cylinder device where the work is being added to the system. The work is not transferring energy to the system, or work is not transferring entropy to the system, but because it's an irreversible process and the entropy of the system changes, it's generating some entropy during that process. Okay, so like compression of a gas or expansion of a gas. And then if we look again at the system plus the surroundings, that the entropy generation is going to be equal to the change in entropy of that system plus the change in entropy of the surroundings. And that's assuming that if we're expanding our boundaries far enough that there's no heat transfer, then those are the equations that we use. So let's do an example. where in this case we have heat transfer through a wall, and we're given a lot of different temperatures, so we need to be careful about how we do this. So we have our wall, which is at 5 degrees Celsius on the outside and 20 degrees Celsius on the inside. Then we're also told that there's a temperature of the air. So it's like 0 degrees Celsius outside and 27 degrees Celsius inside. And by virtue of this temperature difference between the inside and the outside of this house, we're losing heat at a rate of some 1035 watts. So Q dot is 1035 watts through the wall. Okay, so this is like when we previously looked at a heat pump problem. You know, we'd say, okay, our house is 27 degrees Celsius. We want to maintain that temperature. This is the amount of heat that it's losing. How much heat do we need to add, or how much energy do we need to add to our heat pump in order to maintain this temperature? Okay, so this is like looking at another piece of that problem. And now we're going to determine how much entropy is generated via this heat transfer process. So we can determine the rate of entropy generation in the wall itself, and then also look at the system plus the surroundings to find the total entropy generation. Okay, so we're going to assume that the wall is a closed system and that this is a steady state problem, meaning that although the temperature changes from the inside to the outside, so there's some thermal gradient, it's maintaining that same temperature difference. So the wall's not heating up, it's not increasing to, or continuing to increase in temperature or decrease in temperature. The temperature inside is the same, and the temperature outside is the same, those aren't changing. Okay, so this is looking at maybe a period of time in the house where it's balanced. Okay, it's a thermal equilibrium. Even though this temperature is higher than this temperature, there's just a thermal gradient through the wall, so we can still say it's in thermal equilibrium. Okay, so if we perform our energy balance, S dot in minus S dot out plus S dot gen is equal to ds dt. Okay, because it's steady state, this term goes to 0. Do we have any mechanisms of entropy transfer into our system? So if this is our system boundary, is there any entropy being transferred into our system?
Yes.
Yes. How?
Inside heat.
Okay, by a heat transfer, right? So there's heat transferred into the system. We will have entropy in. Is there heat being transferred out of the system? Yes. So we'll have an entropy out. And then entropy generation is just a byproduct of an irreversible process. This is not a reversible process, so we'll have entropy generation as well. So S dot gen is going to be equal to this S dot out plus S dot in, which we can rewrite as Q out over the temperature of the boundary out. So this is minus Q dot in over the temperature of the boundary in. So Q dot doesn't change. It's the heat flux through the wall, so it's 1035 watts divided by what? What is the temperature at which the heat is being transferred out of the wall?
5 degrees.
Okay, 5 degrees Celsius. We can't use Celsius in an equation like this, so we need to convert. What is 5 Celsius? 278 Kelvin. And let's just go ahead and convert this other one. What's 20 Celsius? 293 Kelvin. Okay. What about 0 Celsius? 273 Kelvin. 27 Celsius is 300 Kelvin. Okay. So Q out over the temperature of the boundary out is 278 Kelvin minus Q in. Q in is 1035 watts divided by the temperature at which the heat comes in. And what temperature is that? 293. So it's the boundary of our wall. So we find that our S dot gen in the wall is equal to 0.191 watts per Kelvin. Okay, so now if we want to know the total entropy generation associated with this process, we can expand our boundaries, right? Okay, so we've expanded our boundary to include the system plus the surroundings. So we can just simply use the same equation, the in and the out. So we assume that Q is flowing through the wall into the surroundings, right? So that Q term does not change, but what changes is the temperature at which that heat transfer is being recognized or analyzed. So S dot gen total is going to be equal to 1035 watts over what? So the temperature at which the heat is being transferred out of our system. 273 Kelvin minus 1035 watts over the temperature being transferred in, 300 Kelvin. So the total then is 0.341 watts per Kelvin. Any questions on that? All right. So we've looked at a closed system. Let's now talk about an open system, which will have now mass flowing in and out of the system. So we can transfer entropy via heat, and then now also via mass. So the entropy balance changes slightly, where we have the summation of all of the heat transfer divided by the temperature at which that heat transfer occurs, plus the sum of the mass times the entropy coming in, minus the sum of the mass times the entropy going out, plus this entropy generation term is equal to the change in entropy of the control volume. And we can see that both in the rate form and the non-rate form. So if it's a steady flow system, then this ds dt term goes to 0. And if it's a single stream steady flow system, meaning that there's one inlet and one outlet, it's steady flow, then the mass flow rate in will be equal to the mass flow rate out, so that condenses down. And if it's steady flow, single stream, and adiabatic, then it condenses even further. Okay, so that Q over T, summation of Q over T term goes to 0. So again, be careful about which assumptions you're making. Make sure you use the correct form of the equation, and then recognize the difference between steady flow systems and closed systems, and in particular how mass flow can now contribute to this entropy change of the system. Okay, so we're going to look at a couple of examples of this, and they're going to get increasingly a little bit more difficult because we look at them in slightly different ways. Okay, so in our first case, we have a throttling valve. And what does a throttling valve do? Throttles? Did somebody say it throttles? Okay, what does that mean?
Changes the pressure.
Changes the pressure. What does it do to the pressure? Drops it. Okay, so it causes a significant pressure drop without having to use a work-consuming device. So steam at 7 megapascals and 450 Celsius is throttled in a valve to a pressure of 3 megapascals during a steady flow process. Determine the entropy generated during this process and check if the increase of entropy principle was satisfied. So increase of entropy principle, that we talked about that a while ago. What is that? What does it mean?
The entropy is always increasing.
Yeah, that's exactly it. That entropy is always increasing is the essence of the increase of entropy principle. Okay, so we need to check if it's satisfied. We have this throttling valve, and we're given the initial conditions. So it's steam at 7 megapascals and 450 Celsius. What is the state of that steam? So state 1 is, P1 is 7 megapascals, and T1 is 450 degrees Celsius. What is the state? Okay, superheated vapor. So let's look up some property values. What do you think we'll need? Entropy, right? S1. What is the entropy at state 1? Good practice. Look up properties. You need to practice.
6.6353.
6.6353, what?
Kilojoules over kilogram times Kelvin.
Yeah, kilojoules per kilogram Kelvin. Okay, that's state 1. State 2, we know the pressure is 3 megapascals. Do we know a second property value to fix the state?
Temperature.
Do we?
Steady flow.
Okay, steady flow. You have to think way back to chapter 5 about throttling valves and what's special about them.
The enthalpy remains the same?
Yes, the enthalpy is constant. So H2 is going to be equal to H1, which means we need to look up H1. You still have that, Trenton?
3,288.3
Units?
kilojoules per kilogram.
Okay. So a number is meaningless without units. Kilojoules per kilogram. So that means H2 is equal to H1, which means we're at 3 megapascals, and our enthalpy is this value, 3288.3. How do we figure out where we are on the table, assuming we're not looking at that picture up there that shows us still in the superheated region? We don't have a picture. So what do? We go to the table at 3 megapascals, right? So we can look either at this saturated table or this superheated table, whichever one we choose. If our enthalpy values are somewhere in that table at 3 megapascals, then we're good. Okay, if not, if we're below the lowest enthalpy value, then we have to go to the saturated liquid vapor tables. Okay, so H2 equals to H1. We can look up by interpolation. Look up and interpolate. You don't look up by interpolation, but S2 is 7.00455 kilojoules per kilogram Kelvin. Okay, so we know S1, we know S2. We should be able to determine the entropy generation for this process. Okay, so let's start with the entropy balance, where the sum of Q over T plus the sum of the mass flow rate in times the entropy in minus the sum of the mass flow rate out times the entropy out, okay, plus the entropy generation is equal to this ds dt. Okay, can we simplify this or start canceling things out? Yes. Okay. Do we have any heat transfer? No. A throttling valve is an adiabatic process, so Q is 0. Do we have mass flow in? Yes. Do we have mass flow out? Yes. Entropy generation? Oh boy, yes we do. Is it steady flow?
Yes.
Yeah, so this term goes to 0, not changing with time. Okay, we can simplify this even further. Since there's a single inlet and a single outlet, there's just one mass flow rate times S in minus S out plus S gen is equal to 0, this S dot gen. So we want to solve for this S dot gen and see S dot gen over m dot, because we don't know mass flow rate, but we know that it's equal. So this is going to be equal to lowercase s gen is just equal to s out minus s in, or in this case we called out s2 and in is s1. So we have 7.00455 minus 6.6353 kilojoules per kilogram Kelvin, which gives us 0.36925 kilojoules per kilogram Kelvin. Okay. Did we satisfy the increase of entropy principle?
Yep.
Yes, it's a positive value. Positive entropy generation means we're satisfying the increase of entropy principle. Okay, so our entropy is always increasing. Can never have a negative S-gen. You could have a 0 S-gen, but you can have a negative. Okay, any questions on this example? Okay, so we're going to increase the difficulty slightly. Still not an extremely difficult problem. Similar to what we've done before with mixing chambers in Chapter 5, but now instead of looking solely at enthalpies, we're looking at entropy and how it contributes. Okay, so this problem has a lot going on. We have a family of 4, and each person takes a 5-minute shower every morning. Pretty quick. It's not that quick in my household. The average flow rate through the shower head is 12 liters per minute. City water at 15 Celsius is heated in the water heater to 55 degrees Celsius, and then it's tempered to 42 degrees Celsius, meaning more cold water is added to it to make it a comfortable showering temperature. So we want to determine the amount of entropy generated by this family per year as a result of taking daily showers. Okay. So let's first figure out the total shower time per year for this whole family, right? So we have 4 people times 5 minutes per person per day. 365 days per year. So the total showering time per year is 7,300 minutes per year for all 4 people in that household. Okay, so now we're going to start looking up some property values for these 3 different temperatures of fluid streams, because we have fluid at 15, 55, and 42 degrees Celsius. So at 15 degrees Celsius, we're going to use the saturated liquid properties in the saturated liquid vapor table. So at 15 Celsius, this is flow 1 and 2, so streams 1 and 2. If we draw the picture, I'll draw the picture over here. So we have So we're saying stream 1 is coming from the street. Stream 2 is also coming from the street into the water heater. And then stream 4 is what comes out. Okay, so we're labeling all our streams so as not to get confused. So streams 1 and 2 are at 15 degrees Celsius. If we look up the property values for that, V1 is equal to V sub F at 15 degrees Celsius. What is our property value there? And then we'll also need S1 and H1.
0.001 and 001.
Yeah, 0.001001. meters cubed per kilogram. And what about S1? Okay, S1 is 0.2242 kilojoules per kilogram Kelvin. H1 is 63.01 kilojoules per kilogram. And if any of these values are slightly different, it's because I was using an older edition of the tables when I first did this problem. Okay, so let's look at 42 degrees Celsius now. We look up V, what's the number on it? At 42 degrees Celsius, what's our outlet number or inlet number? 4. Okay, so this is state 4. V4 is 0.001009 meters cubed per kilogram. S4 is 0.5989 kilojoules per kilogram Kelvin. And H4 is 176 kilojoules per kilogram. Okay, so those are the property values at 42 degrees C. Now we need to look at property values at 55 degrees C, and we find V3 is 0.001015 meters cubed per kilogram. S3, 0.7679 kilojoules per kilogram Kelvin. And H3 is 230.3 kilojoules per kilogram. Okay, so we have our time interval, we have all of our property values at each of the 3 different states. We can now set to solving this problem. Okay, we know what in this problem in terms of flow rate. What do we know? Okay, 12 liters per minute. What type of flow rate is that? You almost said it. Yeah, the volumetric flow rate. Do we use volumetric flow rate in our energy balance equations? No, we need an m dot, right? And right now, all we have is the volumetric flow rate of the shower head. So we have V dot 4. But we need m dot 1, 2, 3, and 4. Okay, and in this case, m dot 2 and m dot 3 are going to be the same value, because coming into the water heater and leaving the water heater we'll assume is a steady flow process for m dot 1 and m dot 3. So really we have 3 unknowns and we have 1 known mass flow rate value, so we need a couple of equations to help us out. So let's first find m dot 4 is going to be equal to v dot 4 over the specific volume at state 4. So that's 12 liters per minute multiplied by 1 meter cubed per 1,000 liters is equal to 0.012 meters cubed per minute. And I'm going to leave it in terms of meters cubed per minute. It's not meters cubed, kilogram, sorry. Oh, wait. No. Yeah, that's right. Okay. 0.012 meters cubed per minute is equal to this V dot 4. M dot is V dot 4 over V 4. So this is 0.012 meters cubed per minute divided by the V4, which is 0.001009 meters cubed per kilogram. So this gives us an actual mass flow rate of 11.89 kilograms per minute. That's M4. Okay, so now there are a couple of different systems we can look at to find mass flow rates, right? So we have m dot 1, m dot 2, m dot 3, and m dot 4. So we can perform an energy balance here on that part, that will give us m dot 1, 3, and 4 in an equation. Then we can perform a mass balance on that same part, so we'll have 2 equations, 2 unknowns. We'll be able to go from there. Okay. So the energy balance for here. And I chose here because we're leaving the water heater out of it for now. Okay, so Q dot in minus Q dot out plus work dot in minus work dot out is equal to m dot times h in minus, so it's the sum of the m dot in times h, no, is equal to out minus in. Sum of the mass flow rates out times the h out minus the sum of the mass flow rates in times h in. Okay, and in this case, we have no heat transfer, we have no work interactions, so m dot out, h out is equal to the sum of the mass flow rates in times h in. Okay, so out, we have m dot 4, h4 is equal to m dot 1, h1 plus m dot 3, h3. Okay, so that's one equation. Now we can perform a mass balance on this same part, and we can say m dot 4 is equal to m dot 1 plus m dot 3. So solving for M1 in terms of M3 and M4, so m dot 1 is equal to m dot 4 minus m dot 3. If we sub that back into the original equation, then we can solve for m dot 3. So m dot 3 is equal to m dot 4 times h4 minus h1 over h3 minus h1. Okay, so we sub this back into this original equation, rearranged in terms of m dot 3. So if we plug in all the numbers and solve for that, then we find m dot 3 is equal to 8.03 kilograms per minute. Then we can plug M3 and M4 into those equations, solve for M1, actually just put it back here, and we find that m dot 1 is equal to 3.86 kilograms per minute.
Is it H4 minus H1 or H1 and then M dot 4?
This is H4 minus H1 over H3 minus H1. This is really getting into like the far depths of where you could possibly see from that corner of the room. Okay, so I'll rewrite it up here. We have m dot 1 is equal to 3.86 kilograms per minute. M dot 4 is equal to 11.89 kilograms per minute. And m dot 3 is 8.03 kilograms per minute. And m dot 1, no. Yes, that's fine. Yeah. So m dot 3 is equal to m dot 2. Okay, so I'm going to erase all this. Okay, so we did all that just to find the mass flow rates. We haven't even started talking about entropy yet. So let's look at the entropy generated by the family when we consider this whole thing as our system. Okay, so we're looking at from the street into the house. That whole system is our area of concern to calculate how much entropy is generated. And then we're going to look at it just from the water heater into the house. And if we look at that, we can see how much entropy generation the water heater contributes to the total overall entropy generation. And spoiler alert, it's most of it. Okay, so from the street, we have our entropy balance, so S dot in minus the sum of the S dot out plus S gen is equal to ds dt. So we have this ds dt term goes to 0. That's because it's a steady flow problem, that we don't have any mass accumulation in our system or energy accumulation, so there's no entropy accumulation or entropy change. So we have this m dot 1 S1 plus m dot 2 S2. That's the entropy coming into the system due to the mass flow. We don't have any entropy coming into our system due to heat transfer. We're assuming there's no heat transfer types. Minus m dot 4 S4 plus S gen equals 0. Right, so entropy coming in due to the mass flow, entropy leaving due to the mass flow, plus the S gen is equal to 0. So we can solve for S gen is equal to m dot 4 S4 minus m dot 1 S1 plus m dot 2 S2. Okay, so we have all the values for those, M4, M1, and M2. And we looked up all of our entropy values. So if we put all those numbers in, we find that it's 32,000, wait, no. Hold on. We put all those numbers in, we find that it's 4.46 kilojoules per Kelvin per minute. Okay, so remember the units on m dot are kilograms per minute. So we got rid of kilograms in this kilojoules per kilogram Kelvin, but this is kind of a funky unit. That's okay. So this is how much per minute we are generating entropy as we shower. We now need to multiply it by our time interval to find how much per year for all 4 people in this household. So times 7,300 minutes per year of showering, and we get 32,558 kilowatts per Kelvin per year. So 32,000 kilowatts per Kelvin per year, that's how much we generate by taking showers. Kind of a lot. Okay, so now let's say, okay, we're going to look, instead of looking at the whole system, we're going to look now, again, just at this part from the water heater forward.
How did you get units of watts?
Kilojoules per Kelvin.
That's a rate.
Yeah. Kilowatts.
You had to convert the minutes to seconds.
Hold on. Kilojoules. No, because minutes cancels out here.
Wouldn't
Maybe
it be
it's-
because the mass flow rate is kilograms per second? So that's where you would be kilojoules per second.
Well, this is
Kelvin.
kilograms per second times kilojoules per, kilograms per minute times kilojoules per kilogram Kelvin. So we get kilojoules per Kelvin per minute. So this one is right, but multiplied by minutes per year, then this should be kilojoules per Kelvin per year. You're right. And then we could find the total kilowatts per Kelvin if we took a year and do that. Okay. So 32,000, that's pretty big. Let's just look at from here forward. So we're going to ignore the water heater. We get m dot 1 S1 plus m dot 3 S3 minus m dot 4 S4 plus S dot gen is equal to 0. Okay, so starting with this energy balance, putting in now, instead of M2, S2, we have M3, S3. That's the main term that changes. So instead of looking at the fluid stream before we get to the water heater, we're looking at it after. So we plug in the numbers for that case, and we get 0.0893 kilojoules per Kelvin times a minute, which if we multiply that by the time interval, 7,300 minutes per year, then we get 651.7 kilojoules per Kelvin times a year. So this is the total. This is the total from after the water heater to the street, which means that the water heater itself, the entropy generation due to that is 32,558 minus the 651.7, which gives us 31,906.3 kilojoules per Kelvin per year. So the majority of the entropy generation due to showering is from the water heater. And this is for people taking 5-minute showers, and I doubt very many households have people taking 5-minute showers. Okay, so that's a mixing chamber example where the fluid streams themselves mix together. There's some entropy generation associated with mixing those fluids together. We're now going to look at the case where we have a distinct heat exchanger. I'll leave this here for a minute and not erase it yet because I can tell you're furiously scribbling. So if we look at a heat exchanger example now, where the fluid streams themselves don't mix, but they transfer heat from one to another. We have a couple of different systems that we can analyze. We can analyze the water itself or the oil itself. We can analyze the whole heat exchanger as a system, and we're going to use all three in our analysis today in different ways. So if it's a well-insulated shell and tube heat exchanger used to heat water, CSP given, in the tubes from 20 to 70 Celsius at a rate of 4.5 kilograms per second. So we have the temperature in of the water, temperature out of the water, CSP of the water, and the flow rate of the water. That's nice. They give us everything there. Heat is supplied by hot oil, CSP given, that enters the shell side at 170 Celsius at a rate of 10 kilograms per second. Disregarding any heat loss from the heat exchanger, so assuming the whole thing is adiabatic, we need to determine the exit temperature of the oil and the rate of entropy generation in the heat exchanger. Okay, so all of our information is given for the water. We have a temperature in, temperature out, flow rate, and C sub P. But for the oil, we only have temperature in, C sub P, and the mass flow rate. We don't have a temperature out. We need to solve for it, and then also solve for the rate of entropy generation. Okay, am I safe to erase this now? So how would we go about trying first to determine the exit temperature of the oil? What will affect the oil temperature? How does it increase or decrease, or what do you think is going to happen? Okay, the water is affecting it. How? Okay, so if the water is heating up, then the oil should be cooling down, right? So we would expect the exit temperature of the oil to be lower than the temperature of the inlet. Okay, so if heat is being exchanged between the two fluids, not by direct contact or mixing, but by virtue of this heat exchanger, how do we find the exit temperature?
Energy balance.
Energy balance. Okay, so thinking back to chapter 5 for heat exchangers, we can perform the energy balance on the individual fluids themselves and then set those equal to one another, because the heat that is being removed or the heat is being added to the water is coming from the oil itself. Okay, so let's do first an energy balance on the water. because we have all the information for the water, which means we can solve for Q. So on the water itself, Q in minus Q out, or dots plus work dot in minus work dot out is equal to m dot times H, we'll call it H2 and H1. So H1 is the inlet, H2 is the outlet. Do we have heat being added to our water or removed from our water? Okay, it's being added to the water, so there's a Q in, there is no Q out. Is there any work interaction? No, so we just have a Q in, Q dot in is equal to m dot times H2 minus H1. And in this case, we're given C sub P, so let's use it. It's equal to m dot C sub P times T2 minus T1. Okay, so we can solve for Q. Q dot in is equal to 4.5 kilograms per second, multiplied by C sub P, which is 4.18 kilojoules per kilogram Kelvin, multiplied by the temperature difference. And do I need to convert it to Kelvin? No, because it's a delta T, right? So 70 degrees Celsius minus 20 degrees Celsius. So that's the outlet temperature, or the inlet and the outlet temperature of the water, where 70 is the outlet. Okay, if I were to convert those to Kelvin, I would add 273 and add 273, right? So when you subtract, the difference is going to be the same. It's 50 Celsius or 50 Kelvin. Okay. So Q dot in to the water is equal to 940.5 kilojoules per second, or kilowatts. All right, so now I know Q dot in to the water. I can perform an energy balance on the oil. So it's a similar analysis, but now instead of Q in, I'm going to have a Q out. So I have a negative Q dot out is equal to m dot, and instead of H2 and H1, I'm going to say H4 minus H3, so as not to get confused, which is equal to m dot times C sub P of the oil times T4 minus T3. And in this case, I know T3, right? I know the inlet temperature of the oil, which is 170 degrees Celsius, and I'll solve for the outlet temperature of the oil, because Q out is going to be the same value as Q in. So if I rearrange and solve for that, T4 is equal to negative Q in over m dot C sub P of the oil plus the temperature of the oil. So Q in, which is equal to Q out. Q in of the water is equal to Q out of the oil. So I just sub this in from the previous. So I get negative 940.5 kilojoules per second divided by m dot of the oil, which is 10 kilograms per second, and 2.30 kilojoules per kilogram Kelvin is C sub P. That's messy, sorry. Plus 170 degrees Celsius. So I find that the outlet temperature of the oil is 129 degrees Celsius. Okay, that's part A. Part A is what we did in chapter 5. Okay, we haven't even started talking about the entropy yet. It's just doing chapter 5 stuff. Steady flow, engineering devices, analysis using the energy balance. Yes?
In the node, you put the m dot oil as 4.5.
Okay, I'll fix that. All right, fixed. Okay, so this is just what we've done before. Now, we want to find the rate of entropy generation in the heat exchanger. So if we want to look at it as a whole, we need to think about how we define our system and be careful, right? So if we look at the rate of entropy generation for the fluid stream, let's say we're looking at the rate of entropy generation for the water. Will we have mass flow? We're just looking at the water. Is there mass flow? Yes. Is there heat transfer? Yes, we'll have both of those components. The same thing for the oil. But what if we look at everything all together and look at the entire heat exchanger itself? Do we have mass flow? Where's our system boundary? Right? So we've got some box with mass flowing into it and out of it. And then we've got this other thing with mass flowing in and out. So this is my system. Do I have mass flow crossing my boundaries? Yes, right? Do I have heat transfer crossing my boundaries? No. Okay, so you have to be careful when you analyze these problems that just because you solved for heat transfer previously doesn't mean you now need to plug it into this problem. Yes, if you're solving for the entropy generation of the fluid. Yes. Not if you're looking at it for the whole heat exchanger. So then we look at the entropy balance. On the heat exchanger itself. Okay, so the entire thing. So we've done 3 different systems, right? We looked at the water, we looked at the oil, now we're looking at the entire thing. So the entropy balance is the sum of the Q sub K over T sub K plus the sum of the m dot in, S in, minus sum of m dot out, S out, plus S dot gen is equal to ds dt. Okay, do we have any heat transfer? No. Yeah, we just talked about that. So there's no heat transfer from the heat exchanger to the surroundings. Do we have mass flow in? Yes. Do we have mass flow out? Yes. Do we have entropy generation? Yes. Do we have change in the entropy over time? No, because it's a steady flow problem. So ds dt goes to 0. So we just have the mass flow in due to the water and the oil, mass flow out due to the water, the oil, and this entropy generation term. So we can solve for entropy generation is equal to the mass flow out of the, let's see, the water is K2. So m dot out of the water times S2 plus m dot out of the oil times S4 minus m dot in of the water times S1 minus m dot in of the oil times S3. I have it different on my paper, so I have to think extra hard. So we can combine terms that m dot of the water is a consistent value, so there's m in, m out, but they're the same, so m dot in and m dot out are equal. So it's just m dot of the water times S2 minus S1 plus m dot of the oil times S4 minus S3. The entropy change, when we assume constant specific heats, can be rewritten for an incompressible fluid as m dot H2O multiplied by C sub P natural log of T2 over T1 plus m dot of the oil, C sub P of the oil natural log of T4 over T3.
Why did you say we can do that again?
Assuming constant average specific heats for an incompressible fluid. So meaning the density isn't changing, or specific volume isn't changing. Then if we look back to some of the equations from, I think 2 lectures ago, then we'll find that in there. That's an assumption that can be made. So if we plug in all the numbers for that, mass flow rate of the water is 4.5 kilograms per second. C sub P is 4.18 kilojoules per kilogram Kelvin. Natural log of T2 over T1. Now we have to convert to Kelvin. Okay, so T2 in this case is 70 degrees, so 70 plus 273. T1 is 20 plus 273 to convert to Kelvin, plus the mass flow rate of the oil, which is 10 kilograms per second. C sub P of the oil, which is 2.3 kilojoules per kilogram Kelvin, multiplied by natural log of 129 plus 273 over 170 plus 273. So we're going to find actually that this one will be a negative 2.23. This one will be a positive 2.96. So if we calculate our total entropy generation for the entire heat exchanger, we get 0.730 kilowatts per Kelvin. Perfect timing.